Look at the screen in front of you for a second. If you wear glasses or contact lenses, there is a good chance you have spent years correcting your vision with technology that is basically doing one simple job: bending light before it reaches your eyes. We can build phones that recognize faces, rockets that land themselves, and computers that process billions of calculations every second. But when it comes to human vision, we are still surprisingly dependent on a piece of glass sitting in front of our eyes. That may be starting to change. Researchers in China and Hong Kong have been developing artificial vision technology that takes a very different approach. Instead of simply correcting the light entering the eye, scientists are trying to recreate one of the most important parts of the eye itself, the retina. And if this technology continues to improve, the biggest story may not be about getting better eyesight. It could eventually be about giving humans a completely different way to see the world. Now, there is an important reality check here. This is not a commercial bionic eye that you can order today. It is not a replacement for your smartphone, and it does not mean people are suddenly walking around with digital maps floating in front of their eyes. The technology is still experimental, but the underlying idea is fascinating. Your eye is basically a biological camera. Light enters through the front of the eye, gets focused, and eventually reaches the retina at the back. The retina contains specialized cells that respond to light and help convert what you see into electrical signals. Those signals then travel through the optic nerve toward the brain. That means the retina is not just a piece of tissue sitting inside your eye. It is part of the system that turns light into information. And that creates a major problem when the retina becomes damaged. Glasses can correct certain focusing problems. Contact lenses can do the same thing while sitting directly on the eye. Procedures such as LASIK can reshape the cornea to change how light enters the eye. But none of these technologies can simply replace a retina that has lost its ability to detect light. It is like repairing the lens of a camera when the image sensor inside it no longer works. That is where artificial retina research becomes so interesting. Instead of trying to repair the damaged biological sensor, scientists are exploring whether an electronic material can perform some of the same basic functions. One particularly interesting approach uses extremely small light-sensitive structures known as nanowires. Think about a solar panel. When light reaches a solar cell, it can create an electrical response. Now shrink that basic idea down to an incredibly small scale and arrange huge numbers of light-sensitive structures across a curved surface. That is roughly the engineering concept researchers have been exploring. One of the challenges is the shape of the human eye. A normal camera sensor is usually flat. Your retina is not. It follows the curved interior of the eye. For an artificial system to properly interact with that environment, researchers have to think beyond the traditional flat computer chip. That is why curved artificial retina designs are so important. Researchers have experimented with materials and structures designed to imitate the shape and light response of biological vision systems. Some experimental devices have demonstrated that artificial photodetectors can respond rapidly to changes in light and convert those changes into electrical signals. That sounds technical, but the basic idea is simple. Your biological eye sees light. The artificial system also detects light. The difference is that one uses living cells, while the other uses engineered materials. And that opens a much bigger question. What happens when engineers stop trying to copy the human eye perfectly? What if they start designing an eye that can do things a natural eye cannot? Human vision covers only a small portion of the electromagnetic spectrum. We can see visible light, but we cannot naturally see infrared radiation the way specialized sensors can. That is why thermal cameras and night vision systems exist. Today, if you want to see thermal information, you generally need an external device. A camera, a headset, a sensor, some piece of hardware sitting between you and the world. But artificial photodetectors can potentially be engineered for different wavelengths. That means future artificial vision systems could potentially detect information that ordinary human eyes cannot. And this is where the technology becomes much more than a medical experiment. Imagine a future where an artificial vision system could combine normal visual information with additional digital information. Instead of looking down at your phone to check directions, information could eventually be presented within your field of view. Instead of carrying a separate thermal camera, specialized sensors could potentially provide additional information about the environment. Instead of looking at a physical screen, Some forms of digital information could eventually be delivered through an interface connected directly to the visual system. But we are not there yet. There are enormous problems standing between an impressive laboratory prototype and a safe medical device. The first problem is power. Electronics need energy, and putting electronics close to delicate biological tissue creates a serious engineering challenge. A smartphone can get warm when you use it heavily. You can simply put the phone down. You cannot do that with an implant. Researchers therefore have to think about extremely low-power electronics, wireless energy transfer, materials that remain stable inside the body, and ways to prevent unwanted heating. Then there is another problem that may be even harder. The human body is not an empty container waiting for technology. It is a living system. When you introduce a foreign material into the body, the surrounding tissue can react to it. Long-term implants have to be designed so that they can remain functional without causing unacceptable damage or inflammation. And connecting an artificial sensor to the visual pathway is another enormous challenge. Detecting light is one thing. Turning that information into signals the nervous system can actually interpret is something else entirely. That is why headlines about an artificial eye need to be treated carefully. A laboratory device demonstrating light detection is not the same thing as restoring normal human vision. And restoring limited vision is very different from creating a digital interface inside someone's visual system. Still, the direction of research matters. Because every time engineers learn how to make an artificial sensor smaller, more sensitive, more flexible, and more compatible with biological tissue, they move one step closer to something that once sounded impossible. The first goal is medical. Help people whose biological vision has been damaged. But the same technologies could eventually lead to something much more ambitious. A future where the boundary between a human eye and an electronic sensor becomes harder to define. And that is where this story gets truly interesting. Because the future of screens may not be about making the screen smaller. It may be about making the screen disappear. And if that sounds like science fiction, there is one important detail to remember. The technology does not have to become a perfect replacement for the human eye to change the future. It only needs to become good enough to add something to human vision. Imagine looking at a road and seeing useful information appear without taking your phone out of your pocket. Imagine a navigation system showing you where to turn while your hands remain completely free. Imagine a technician looking at a machine and seeing important measurements without carrying a separate display. Or imagine someone with severe vision loss receiving useful visual information from an artificial sensor. These are very different applications, but they all come from the same basic idea. Move information closer to the visual system. That is a major reason companies in the United States and elsewhere are investing so heavily in augmented and spatial computing. The current approach is to put more technology around your eyes. Headsets, cameras, displays, sensors, processors, batteries. The goal is to create a computer that can understand the environment and place digital information on top of it. But there is another possible direction. Instead of building a better computer that sits on your face, engineers could eventually build a smaller system that interacts directly with the biological vision pathway. That would completely change the hardware equation. Today, if your phone battery dies, your digital world disappears. If your headset becomes uncomfortable, you take it off. If you want to stop looking at a screen, you can simply look away. An implanted visual interface would raise completely different questions. Who controls the information? Where does the data come from? How is the device updated? What happens if the connection fails? And perhaps most importantly, who gets access to what the device sees? Because an advanced visual implant would not just receive information. A sufficiently sophisticated system could potentially collect information too. Think about how much your phone already knows about you. It can record where you go. It can learn what you search for. It can measure how long you use an application. Now imagine a device that can understand aspects of your visual attention. That creates an entirely new category of privacy concerns. Your eyes constantly move around your environment. You look at faces. You look at products. You look at road signs. You look at advertisements. You look at things without consciously thinking about it. An advanced eye tracking system could potentially turn some of those movements into data. That does not mean today's experimental artificial retina devices are secretly recording everything a person sees. They are not. But as visual technology becomes more connected, privacy will become one of the biggest questions engineers and regulators have to solve. And there is another area where this technology could become extremely important: medicine. For someone with severe retinal damage, even limited artificial vision could have a huge impact. Being able to detect light, recognize shapes, or identify movement could potentially make everyday tasks easier. That is a very different goal from giving someone perfect eyesight. Medical technology often develops in small steps. First, researchers prove that a basic function is possible. Then they improve the device. Then they test safety. Then they conduct controlled clinical studies. Only after years of evidence can a technology potentially reach large numbers of patients. That is the path artificial vision will have to follow. And this is where some of the more dramatic claims surrounding bionic eyes need to be separated from reality. A prototype is not a finished product. A device tested in a laboratory is not automatically safe for long-term implantation. And detecting infrared light with an artificial sensor does not mean a person can instantly walk into a dark room and see everything like a thermal camera. There are multiple layers between detecting a signal and creating a useful visual experience inside the brain. The sensor has to detect information. The electronics have to process it. The signal has to reach the appropriate biological pathway. And the brain has to learn how to interpret that signal. The human visual system is incredibly complicated. So the real breakthrough may not arrive as one dramatic moment. It could come through dozens of smaller improvements over many years. Better materials, smaller electronics, more efficient power systems, more precise interfaces, better signal processing, safer implantation methods, and better understanding of how the brain interprets artificial visual signals. There is also a manufacturing challenge. Building a tiny experimental device in a research environment is one thing. Producing thousands or millions of identical medical implants is another. Every component has to meet extremely strict requirements. The materials must be consistent. The electronics must remain stable. The manufacturing process has to be extremely precise. And the final device has to survive years inside a living human body. That is a completely different challenge from building a consumer gadget. Then there is regulation. A medical implant cannot simply move from a laboratory into hospitals because a demonstration looks impressive. It needs extensive testing. Researchers need to understand potential risks. They need to examine long-term reliability. They need to study what happens if a component stops working. And regulators need enough evidence to decide whether the benefits outweigh the risks. That process can take years. So no, the smartphone is not about to disappear tomorrow. Neither are glasses. Neither are normal computer screens. And today's artificial retina research does not mean people are suddenly going to receive digital vision upgrades at their local hospital. But the direction is still worth watching, because there is a bigger technology race happening underneath all of this. For decades, computers became smaller and smaller. First they filled rooms. Then they sat on desks. Then they fit into our pockets. Then we started wearing them. The next question is obvious. What happens when the computer becomes part of us? That is the long-term possibility behind advanced human-machine interfaces. And the eye is one of the most interesting places to explore it because vision is how humans receive enormous amounts of information every second. If technology can safely communicate with the visual system, the possibilities become much larger than simply correcting eyesight. It could change how we navigate, how we work, how we interact with machines, how people with disabilities access information, and eventually, perhaps, how we interact with digital environments. But there is an important line that should never be ignored. Technology should not be judged only by what it can do. It also has to be judged by whether it can be used safely, voluntarily, and responsibly. A future where people can restore lost vision could be extraordinary. A future where people can enhance their senses could be transformative. But a future where private visual information can be collected without meaningful control would create serious problems. The real challenge is therefore not simply building a better artificial eye. It is building one that people can trust. And that may be harder than the engineering itself. For now, the most realistic way to look at these Chinese and international research efforts is as an early step toward a much larger field. Scientists are learning how artificial materials can detect light. Engineers are learning how to make those materials flexible and extremely small. Researchers are studying how artificial signals can interact with biological vision systems. And every improvement moves the technology a little closer to practical applications. Maybe the first major success will be helping someone regain a small amount of useful vision. Maybe the next generation will make artificial vision more natural. And much further down the road, completely new forms of visual interfaces could emerge. We do not know exactly where the technology will end up. But one thing is becoming increasingly clear. The screen in front of you is not the final form of human-computer interaction. For decades, we accepted a simple arrangement. The computer stays outside. The screen stays in front of us. Our eyes look at it. Our hands control it. But technology keeps pushing those boundaries closer together. The computer moved from the room to the desk, from the desk to the pocket, from the pocket to the wrist, then to the face. The next step may be much more personal. The technology could move from something we wear to something that interacts directly with our biology. And if that happens, the biggest change will not simply be that we get better vision. It will be that the definition of a screen starts to disappear. So the next time you look at your phone, think about what you are actually looking at. A small rectangle of glass is currently sitting between you and an enormous digital world. But researchers are exploring a future where that rectangle may no longer be necessary. The ultimate display may not sit on your desk. It may not sit in your pocket. It may not even sit on your face. It could eventually become part of the visual system itself. And if scientists can make that future safe and practical, the way humans see technology may never be the same again.